There is a moment captured on film that I think about more than almost anything else from my entire career. A journalist once asked me a simple question. He said, "Can you explain in a simple way why it is that two magnets or two electrons repel each other? Why does this happen?" And I sat there and I told him I couldn't answer that in the way he wanted. And then he asked something even more dangerous. He asked in the most general sense, what makes anything attract or repel anything else? What is force, really? And after a long pause, I said something that surprised even me when I heard myself say it. I said, "I don't know." I want you to sit with that for a second. A man who spent his entire life studying the fundamental forces of nature, who won a Nobel Prize for figuring out how light and matter interact at the deepest level anyone had ever calculated, looked directly into a camera and said the three words that most people spend their whole lives trying to avoid saying out loud. I don't know. And here is what I want to show you today. That sentence was not a failure. It was not an embarrassment. It was, I believe, the most honest and the most scientific thing I ever said in front of a camera. And once you understand why I said it, and why I had to say it, you are going to see science, and maybe your own life, completely differently. Let's go back to the question itself, because the question is more interesting than people realize. Why do two electrons repel each other? Most people expect there to be a satisfying mechanical answer underneath. Something like, well, there are tiny hooks on the electrons, or there's some kind of pressure, or there's a fluid being squeezed out from between them. People want a picture. They want a mechanism made of familiar parts, the same way a clock is made of gears, or an engine is made of pistons. But when you actually go looking for that mechanism in the case of electromagnetic repulsion, you don't find one. What you find instead is a mathematical description of incredible precision. Two electrons repel each other with a force that is inversely proportional to the square of the distance between them, and directly proportional to the product of their charges. I can write that down. I can calculate it to 10 decimal places. I can predict exactly how strong the force will be at any distance you choose. I can use that equation to build transistors, to design particle accelerators, to explain why your hand doesn't pass through a table. The mathematics works. It works better than almost anything else human beings have ever discovered. But if you ask me what is actually happening, what is the mechanism, what is physically occurring in the space between those two electrons that produces this push, I have to tell you something uncomfortable. I don't know. Nobody knows. Not because we haven't worked hard enough. Not because the answer is hiding somewhere waiting to be found by a smarter person. We don't know because the question itself, the way most people ask it, assumes that there must be a familiar mechanical story underneath every fundamental force. And there doesn't have to be. There might not be. Let me walk you through this more carefully because I think this is where people get confused about what science actually does. When a child asks why a ball falls when you drop it, you can say gravity pulls it down. The child accepts that. Then the child asks, why does gravity pull it down? Now you have to go further. You can talk about mass curving space-time, about Einstein's general relativity, about geodesics and curved geometry. The child, if they're persistent, asks, why does mass curve space-time? And now you have hit a wall. There is no further answer. Mass curving space-time is, as far as we currently understand the universe, a fundamental fact about how reality is constructed. It is not built out of something simpler. It just is the way things are. This happens with every chain of why questions in physics if you follow it far enough. You ask why and why and why and eventually arrive at a small number of basic facts. The fundamental forces, the fundamental particles, the basic structure of space-time itself. And at that point, the only honest answer is, this is simply how nature behaves. We can describe it with extraordinary precision. We can predict everything that follows from it. But we cannot explain it in terms of something even more basic, because there is no something more basic. We have reached the floor. I want to be very precise about what this means, because I think people often hear this and think it sounds like science giving up, throwing its hands in the air and saying, who knows, it's a mystery. That is not what is happening, and it is the opposite of giving up. Watch carefully. When I say I don't know what force really is, I am not saying the equations are wrong or incomplete in some practical sense. The equations are extraordinarily well tested. Quantum electrodynamics, the theory that describes how electrons and photons interact, has been verified to a precision of about 1 part in a billion. That is the kind of precision where if you measured the distance from New York to Los Angeles, the theory would predict it correctly to within the width of a human hair. This is not a weak theory. This is one of the most successful theories in the history of human thought. But precision of prediction and depth of understanding are two completely different things, and the great trap that most people fall into, scientists included sometimes, is confusing the two. You can have a theory that predicts everything perfectly and still not have an answer to the question, but what is really going on underneath? The mathematics tells you how nature behaves. It does not necessarily tell you what nature fundamentally is, in the sense of giving you a familiar mechanical picture you can hold in your mind the way you hold a picture of gears turning or water flowing. This is the distinction I was trying to make in that interview, and it's a distinction most people never get the chance to think about carefully, because in daily life, everything seems to have a story underneath it. Why did the car stop? Because the brakes were applied, which pushed pads against the rotors, which created friction, which converted kinetic energy into heat. Every step in that explanation refers to something familiar, something you can picture. Pads, pressure, friction, heat. Each piece connects to something you already understand from direct bodily experience. But fundamental physics does not work that way, and it never will, because if it did, the things we call fundamental wouldn't actually be fundamental. They would just be another layer waiting to be explained by something even more basic. The whole point of finding something fundamental is that you have reached a layer where there is nothing more basic underneath, and when you reach that layer, asking for a familiar mechanical explanation is, in a strange way, asking for something that cannot exist by definition, because familiar mechanical explanations are themselves built out of the fundamental thing you are asking about. This is exactly the track with electromagnetic force. Your intuition about pushing and pulling, about contact, about solid objects bumping into each other, that entire intuition is itself a consequence of electromagnetic forces operating at the atomic scale. When you push a chair, you feel resistance because the electrons in your hand and the electrons in the chair repel each other electromagnetically, and neither set of electrons can occupy the same space as the other. Your whole felt sense of solidity, of pushing, of contact, all of it is built out of electromagnetic repulsion. So when you ask me to explain electromagnetic repulsion in terms of pushing and contact, you are asking me to explain the foundation in terms of the building that is built on top of the foundation. It cannot be done. Not because I am unable to explain it well enough, because the request itself does not make logical sense once you see clearly what is being asked. So when I said I don't know, what I actually meant was something much more precise than it sounded. I meant I do not have, and nobody has, and possibly nobody ever will have, a description of fundamental force in terms of something more familiar and more basic, because fundamental force is not built out of anything more familiar or more basic. It is one of the bedrock facts the universe is constructed from. I know how it behaves with extraordinary precision. I do not know what it is in the deeper sense you are asking for, because that deeper sense may not exist for fundamental things. It may be a category error to even ask the question that way. Now here's why I think saying I don't know was the most honest thing I could have said, and why I think it matters far beyond physics. There is enormous social pressure, especially for someone in my position, to always have an answer. People expect a famous physicist to be able to explain anything, to have some clever analogy ready for every question, to never be caught without a satisfying response. And it would have been easy in that interview to make something up. I could have said something about tiny invisible springs, or fields like rubber sheets, or some other comforting picture that sounds like an explanation but doesn't actually correspond to anything physically real at the fundamental level. People would have nodded, they would have felt satisfied, and they would have walked away with a false picture of reality, believing they understood something they did not actually understand, because I gave them a story instead of the truth. I have always believed that the first principle of science, and frankly the first principle of an honest life, is that you must not fool yourself, and you are the easiest person in the world to fool. The moment you start accepting comfortable stories instead of admitting the limits of what is actually known, you have begun fooling yourself, and once you start, it becomes very hard to stop. Saying I don't know when you genuinely don't know is not a weakness. It is one of the most disciplined and difficult things a thinking person can do, because every instinct in you wants to fill the silence with something, anything, that sounds like an answer. And I think this generalizes far beyond physics, which is part of why that moment in the interview stuck with so many people. We live in a culture that treats not knowing as a failure, as something to be embarrassed about, something to cover up quickly with a confident-sounding guess. Children learn this early. They learn that admitting you don't know the answer in front of the class feels worse than guessing wrong. Adults carry this into every part of their lives. People will confidently explain economic policy or nutrition or history or how their own emotions work, using stories that sound complete and satisfying but that actually have no real mechanism underneath them at all. They are doing exactly what I refused to do in that interview. They are mistaking a comforting story for genuine understanding. The discipline of science, at its best, is the discipline of refusing to do that. It is the willingness to say, here is exactly what we know, here is exactly how confident we are in it, and here is the precise boundary beyond which we do not know, and we will not pretend otherwise just to make you or ourselves feel more comfortable. That boundary moves over time. Things that were once mysteries become understood. The wave nature of light, the structure of the atom, the expansion of the universe, all of these were once beyond that boundary, and patient, careful work moved the boundary outward. But there is always a boundary, there always will be. And the question is not whether you will eventually reach a place where you must say, I don't know. You will. The question is whether you have the honesty to say it clearly when you get there, instead of dressing up your ignorance in language that makes it sound like knowledge. When I told that interviewer I couldn't explain force in the way he wanted, and that ultimately I had to say I don't know what it really is beneath the mathematics, I was not failing to do my job. I was doing my job in the only way that has any integrity. I was showing you exactly where the solid ground of human knowledge ends and the unknown begins, instead of paving over that edge with a comfortable illusion. So here is what I want you to take from this. The next time you are asked a question you genuinely cannot answer, whether it is about physics, or about your own life, or about something you deeply care about, notice the impulse to fill the silence with a guess dressed up as certainty, and then consider doing the harder, more honest thing. Consider saying the 3 words that took me a long pause and a great deal of internal resistance to say on camera that day. I don't know, not as a surrender, as the beginning of the only kind of understanding that is ever actually worth having, the kind built on knowing exactly what you know and exactly what you don't. If you want to keep seeing the world for what it actually is, not what it appears to be, subscribe. That's what this channel is for.